Welcome back everyone. Till now we were looking into state feedback for MIMO systems. Now comes another question. So I had already answered this question for you, what happens if the system is uncontrollable, and now we are asking this question, how will the system know where to go? Notice that in this case whatever we are doing, the control once we feed in the control law, the system is x dot equal to a minus bk into x, which means that once I have this, my xt gets fixed, xt will be e to the power of a minus bk whole of t x naught, and my y also get fixed because y is nothing but this plus d of u again, but d of u also will get changed. So this will be my y. So c minus dk whole into e to the power of a minus bk whole into t x naught. So this is my output. And notice here that the output, once you have fixed k, depends only on the initial condition, and you do not know what will be the final value of the output. Because you see, if you remember in PID case, what we used to do when we had a PID controllers, what we used to do was we gave a reference input to the system, right, and we wanted that the output of our system should follow the reference or should reach the reference. So if I give 5 step input as step input, I want that my output should also reach to 5. But in this case you see the output yt is equal to this expression here. Now there is no way you know what is the final value of the output. So the problem statement that we actually have is find a state feedback control such that the steady state value of the output yt is equal to c. This is actually the main control problem. Till now what we were doing was we were changing the eigenvalues of the system, okay, but as a control engineer the main problem is that I want my output to reach to a certain point, right. For example, the quadrotor example that we always take, right, that it has to reach to a particular altitude, okay, but in this setup that we are working on, that state feedback that I had talked about, nowhere I have talked about this idea that the output should reach to a particular point. So now I am bringing that in, okay. So the problem statement is find a state feedback control such that the steady state value of the output yt is equal to c, c being a constant here. Now how do we ensure that yt will go to c, and that is what we will look into now. Now if we use the control law u equal to minus kx, then you can see that the x dot will come out to be this expression and yt will be this, which means my output expression is this, and as I have just now motivated that in no way I know that y of infinity, which is basically the steady state value of the output, this is equal to c. How do I ensure that this expression will give me c? So what is the idea that we should use? So in place of u equal to minus kx, we will use the control law u equal to minus kx plus nr. So here this is, let me talk about CISO systems only here now. So this is a 1 cross 1 signal, and then this will also become 1 cross 1, okay. Here k was 1 cross n and here x is n cross 1. Okay, so my control law now is minus kx plus nr. I am adding a extra term. Now how does it change the system? So if I put this control law into the system, so my new equation becomes x dot equal to ax plus bu. So in place of u I am putting this expression, so this becomes minus bkx plus bnr, right. You can see that hopefully. So x dot equal to ax plus b, and then here we are replacing it with this. So therefore this becomes a minus bk whole into x plus this expression, and my yt will become something like this, because again here if I put that control law, then it becomes cx plus d minus kx plus nr, and so this is nothing but c minus dk whole into x plus dnr. This is what I am writing. Now once I have written that, now notice what will be the, what will happen at steady state. So what will happen at steady state? At steady state x dot will be 0 because it is steady state, x has settled down, okay, there are no changes in x anymore. So, x dot will become 0, x infinity, the value of steady state value, let us assume that the steady state value is xss, and we want that the output's final value should be c. Okay. Remember what I am doing, I want that at t tending to infinity my output should be c. Okay. So, that is why I am analyzing x dot equal to ax plus bu at t tending to infinity. So, at infinity what will happen? So, the states will settle down, because the states keeps on changing only at the beginning, right, that is the transient phase. So, once it settles down, then x dot will be 0, there are no changes in the state. So, we will have x dot equal to 0. Then what will I take for x infinity? Now, where will the state settle down? I do not know, let me call it xss, okay. And y infinity, my desire is that y infinity should be c, some constant value. Let us see what happens if I plug this into the equations. So, once I plug this into this equation, so at steady state what will happen? If I plug this in here, the left hand side becomes 0, and then we have a minus bk xss plus b and r. So, from here xss will come out to be a minus bk inverse b and r with a negative sign. Now, can I invert this? Yes, I can invert this, because I have chosen a k such that the eigenvalues are on the left half of the complex plane, say. Okay. I can always choose this k so that the a minus bk is invertible. So, if this is invertible, of course, if you have chosen a k such that a minus bk is not invertible, then we will have a problem. But in this case, we are choosing a case where a minus bk is invertible. So, this is the expression that we get. Now, what about the output expression? The output expression is yss equal to c minus dk, xt becomes xss plus d and r. Okay. And now, xss we can replace from this equation to get an expression of this form, which in turn comes out to be this. Now, notice this expression carefully. I want that my output should be such that I get a c here. So, what will happen? If I choose n to be equal to c times the inverse of this matrix, negative of c times the inverse of this matrix. So, let me call this matrix to be, let me just give some name to this, let me call it delta. Okay. So, now if I take minus c times delta inverse in place of n, then what do I get? I will get minus delta, n is being replaced by minus c into delta inverse and RT, and so I get this to be equal to c RT. And now, if I choose my RT to be a step function, so basically I am saying that you take a u step t here, I am done. If you take the control law to be u equal to minus kx plus, in place of n, if you put minus c delta inverse u step, if you take this type of a control law, then you will be able to reach the steady state value that you wanted to reach. We will look into a simple simulation now and see that this is true. So, let us take this example, say a is equal to 1 0 minus 5 minus 6, b is equal to 1 1, c is equal to 1 2, d is 0. Okay. And if you check the eigenvalues of this matrix is minus 6 and 1, which means the system to start off with is unstable. Say I come up with a feedback matrix of k equal to 10 minus 1. So, in that case, if you check, if I use u equal to minus kx as the control law, then the eigenvalues will come up to be minus 12 and minus 4. So, now I have stabilized the system. Now, suppose that I want that the system should go to the output of the system should go to suppose 1. In that case, I want to give a control law of the form u equal to minus kx plus nr. So, n I will have to choose carefully. So, we have already seen that n has to be this expression, inverse of this expression or negative of inverse of this expression. So, I will choose that. So, n is equal to, n will be equal to minus of inverse of c minus d into k. Although d is 0 in this case, you can even get rid of d, but let me just write it down for say completeness, b into k inverse into b plus d. So, this is your n now. So, now we will try to simulate the system using Simulink. So, in Simulink, let us try to model the system. So, first we will need an integrator. So, here is your integrator, then we will take a gain block, control R will rotate this gain block. So, we take the A matrix here. Okay. So, basically I am trying to simulate the block diagram of x dot equal to x plus b u. So, that means that you will have an integrator and then you will have to feed back the A. So, here A I am taking and then I will use a summer here. If I feed it back, this will be your system. So, this is here x dot is coming in, it is getting integrated. So, you have x here. So, A x and then I need b u also. So, gain, double click on it, b. So, this gives you A x plus b u. So, u can be a step input here. So, let me give a step input here and then I can have the output as C x plus d u. In this case, since I have not taken d, I will not use d, instead I will just put C and then I can use a scope here to see the output. The only thing that you have to be careful about here is that you see when this signal is coming into A into that signal is a vector multiplication, not a scalar multiplication. So, A is a matrix here. So, therefore, when you double click here you will see the multiplication type you can choose. So, the multiplication has to be matrix multiplication k into u. Similarly, for B, double click on that, you have to change the multiplication type. So, I have changed that. Now, if I want to apply a feedback to this system, I will need another gain block, control R. So, it gets rotated. So, I will take k here and in other words I will take minus k here because my control law is minus k x plus n r. So, minus k matrix multiplication and so you can put it here. So, our control law is u equal to minus k x plus n r. So, this we have minus k x here, n r we will have a gain block. So, let us take that gain block, let us put n here, again this is matrix multiplication. So, this and then we will need a summer here. And we will have an R. So, R we will give it as a step input here. So, this is the setup that we have. Let us have a look at the output. You can notice that the output is 1 now. If you want to change the output now, you can just go ahead and change the final value here to say maybe 4. okay, and then if you go ahead and check, you will see that the output should go to 4. Okay. Note that the if you look at the step input, I have taken step time to be at 1. So, you can make it 0 also. Basically, the reference signal is from goes from 0 to 4 at t equal to 0. So, now if you go ahead and check the output, you can see. So, it just follows it, and at steady state the output has become 4. This could be done because you chose n to be the negative of inverse of this quantity, and as a result of this multiplication became 1 or identity, and then YSS was equal to RT. So, whatever RT you choose step input, that will be the output now. Now that you have seen the simulation, you know what type of a control law we should use, okay, so that we can actually get to a particular steady state value for the output. Okay. Now, the question that is left with us is this last question, that how do I find out this x, because in order to implement minus kx, I need to know the states of the system. Now, will the states of the system be always available to us? That is not true actually. States of the system may not be always available to you. So, how do I find out the states of the system? And for that we will have to go into something called observers, and that we will take up in the next lecture. Thank you.